Hi everyone, hope you're all well. If you haven't been following, I'm going through this book, Practical Electronics for Inventors. Main reason I'm going through it is I'm a bit behind on my studies for my second year of electrical engineering, so I need to use this book to try and catch up. I'm currently learning about AC electronics and I'm struggling a little bit, so I'm getting through it slowly. So if you're in that kind of place as well, then tag along. Let's do this together. So in the last video, I learned a bit about amplitude of an AC waveform. So I'm just going to pick up from here. All right, I think I touched on frequencies. I did, yeah. And then I got onto these basically examples. So let's do let's do this without looking at the answer. So example here, what is the period of a 60 hertz AC current? Okay. So I'm not messing about today, straight into it. So the way that you convert period I really can't spell. The way that you convert period to frequency is by doing 1 over frequency, right? And the way that you convert frequency is by doing 1 over period, if I'm not mistaken. Right? So if we're saying that, let's say we got a question here, and we're saying what is the period of a... So I think I'll be able to do this. Let's see, we'll see in a second. But what I want to know is I want to understand actually what it means, the period of a 60 hertz AC current. Does that mean how long it takes to do one cycle? I think that's what it means. I think that basically means how long does a 60 hertz sine wave take to do just one cycle, meaning this. I think that's what that means. So if we're saying that period is equal to, what's period? Is period is t, as you can see here. Period is t. Okay, so period is t for time, I assume, and we're saying that it's 1 over frequency, which is 1 over 60, which is, calculator, 1 divided by 60, so 0.0166 recurring, right? So that's basically, you got 1 second here, then you got 100 milliseconds, right? And then you got 16 milliseconds. Is that right? Are we talking 16.6 milliseconds? I don't know if my SI units there are correct, but let's say they are 16.6 milliseconds. So it takes 16, basically 17 milliseconds, you could say 17 milliseconds to do one cycle. I believe that's what that means. Let's see. So 0.0167. Oh yeah, that's how I should round it up. 0.06. So 0.016 seconds. So what's 0.016 seconds in milliseconds? So is that 16 seconds to milliseconds? Yeah, I was right. 16.7 milliseconds. Okay, that's cool. I'm very glad I understand that. So let me just rub this out and just put. Oh, I've gone to the top. iPad is a bit of a bummer sometimes. Okay. 16.7 milliseconds to do one cycle. Okay. I haven't really confirmed that it is to do one cycle, but again, I believe that's what that means. I think so anyways. Okay. Decided to take off my watch now. You know when it's getting heavy, you gotta take your watch off. Alright, so what is the frequency of an AC voltage that has a period of 2 nanoseconds? Hang on a minute. What's the frequency? What are we asking here? Okay, so we're asking. Okay, so what we're saying here in this question, let's just write it down. What is the frequency of an AC voltage that has period of 2 nanoseconds. I'm actually feeling more confident on this now, so hopefully, I get a lot more studying done. Because the thing is, when you're not confident, you really don't want to study, because who wants to just sit there and be wrong all day? Especially when you're recording a video for YouTube, and potentially hundreds or thousands of people might see it and go, "Well, you're a bit of an idiot." So yeah, the fact that I'm starting to get it more now, hopefully, should mean that I do it more. And then obviously, the more I do it, the faster I'll get it, and the quicker I'll be able to actually do well in my module. So, all right. So what this question here is saying is that if a waveform if it takes 2 nanoseconds to do one cycle, right? Then how many cycles per second? I believe that's basically what the question is saying. What is the frequency of an AC voltage that has a period of 2 nanoseconds? So this frequency is equal to 1 over time, and then which is equal to 1 over 2 nanoseconds. How do I do nanoseconds? You're talking 0.0. Okay, so that's 20 milliseconds. 2 milliseconds. Nano is an extra 1, 2. Okay, wait. 1, 2, 3, 4, 5, 6. I believe that's right. Gonna have to check. So let's do nanoseconds to seconds. 0.2. 2 to the 10. I still can't really draw it like that. I don't like the engineering. Can't remember how to do that. Just give me it written properly, man. Bloody hell. 2 to the power of minus 10. How many zeros is that? 2 to the power of minus 10. Ah, come on, man. Just give me exactly what it is. Okay, there you go. So 2 to the power of minus 10 is how many zeros? I believe it should be 9, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 zeros and then 2. Okay. So it's equal to 0.01, 2, 3, 4, 5, 6, 7, 8, 9, 2. Okay, so once you do that on the calculator, let's just move this smaller. Okay. So 1 divided by 0.123456789 2. What the hell? 50, like, I don't know. How many zeros is that? 5, and then 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9. I feel like I've done something wrong there. How are we having 5 billion? Okay. So it's right. It's 5 billion hertz. Man, I've got to get comfortable with these SI units again. I always learn them and then I forget them because I don't use them once I learn them. This is why I need consistent study, especially in particular about the theory. Okay. So we've got 5 billion hertz. Then how are you getting to mega? Ugh, let's just get an SI unit chart. Drive me nuts. SI unit chart. Okay. So mega is 1 million. So I can just knock off a million, right? So I take this, put it over here. Anyways, so I can knock off a million, and then I could just say 5,000, and then replace that whole million with an M. So that basically equals 5,000 megahertz. Is that right? Yeah. Oh, 500, huh? Mega is a million. So only knock off five. Ugh, I'm not comfortable with this converting through the units. Um, why am I only knocking off five and not six? Okay, let's just go to the ones that we know. So we've got 10. If we wanted to do times 10 to the power of 2, we're already at 1, so I don't know. I don't know how to work it out, to be honest. I just have to trust that whatever, fine. Obviously the book's right, I'm not right. Yeah, I don't get it. Anyways, 500 megahertz. It's one of those. Again, the frustrating thing about university here is that like I could never learn SI units and still, get a top class degree, which is just a bit crazy how these things kind of work, but is what it is. Anyways, the frequency of an alternating current or voltage in electronics varies over a wide range from a few cycles per second to billions of cycles per second. So like in this instance here, right? To make life easier, prefixes. Okay, here we go. Prefixes are used to express large frequencies and small periods. For example, 1,000 hertz is equal to 1 kilohertz. Okay, that's a better way of me understanding it. Yeah, of course, yeah. A million hertz is 1 megahertz, right? Just like a million. So kilowatts I'm comfortable with because that's been my job for the last few years. I'm very comfortable with, dealing with kilowatt hours. So I just need to think about the same thing. Obviously, as well, there's excuse me, bloody yawning all over the gaff. There's obviously gigabytes as well. So obviously 1 gigabyte is a million bytes. Oh sorry, 1 gigabyte is a billion bytes, and is a million megabytes. Okay, 1 billion hertz is 1 gigahertz. 1 trillion hertz is 1 terahertz. Okay, so let's just write this down because I do need to get it in my head. 1,000 hertz is equal to 1 kilohertz. Yes. Okay. And a million hertz. I don't know why I just did that. A million hertz is equal to 1 million megahertz. And a billion is equal to 1 gigahertz. And a trillion 1 terahertz. Okay, so you got 1,000 million billion trillion. Okay. Okay, so we got for units smaller than 1, as in the measurements of a period. As in the measurements of a period. Period. Okay. The basic unit of a second can become milliseconds, 1,000th of a second. Okay, so millisecond is 0.001. Millisecond is equal to 1,000th of a second. Or another way of saying that is one over 1,000, right? Seconds. The basic unit of a second can become milliseconds. 1,000th of a second, or ms. Microsecond, which is 1 millionth of a second. So how would I do this? 0.00, and then 3 more zeros. 1. So 5, right? 1, 2, 4, 5. Yep. And then so what would that be? Oh, this wouldn't be milliseconds. This would be seconds. And this is seconds as well. And that gives you 1 millionth of a second. 1 millionth of a second. Or it's 1 second divided by a million, right? Let me just do that on my calculator. So 1 second divided by a million. 2, 3, 4, 5, 6. And that should give you 5. 2, 4, 5. Yeah, got it. Okay, and so that is okay. Wait, let's make some space. Okay, so 1,000th of a second is 1 millisecond, and then a microsecond is that micro symbol, the U symbol. Need to try this is what I like about the iPad. I can make space on it here. Okay, this is equal to 1 microsecond. Okay, and then you've got a nanosecond. I don't even know how I'm gonna go. That's a lot of zeros. So how many zeros is that? 5, so it'll be 8 zeros. 0.123456781 seconds is equal to 1 billionth of a second, which is equal to 1 over a billion seconds, which is equal to 1 nanosecond. Okay, 1 nanosecond, and then pico is a trillion. Okay, am I gonna have space? Let's move this up. Okay. I'm being a bit meticulous, I know. Apologies. If I don't do this now, I'm not gonna do it. So billionth of a second, and then we've got a trillionth of a second, a picosecond. Which is PS. Okay. So we got 0 point and then a trillion. So that's like I don't even know how many zeros. So we had 5 zeros there. We got 8 zeros there. So that's 11 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1 seconds, which is equal to 1 trillionth of a second, which is equal to 1 divided by a trillion seconds, which is 1 PS. Okay, I'm comfortable with that. Okay, so we move on to phase now. So just to get a reminder, I've gone over amplitude. So all of this is amplitude, 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 and then we went on to frequency and period, and then now we're on to phase. So if I think about it, amplitude is I can't really even describe it. It's like how large or small the voltage or current is. So like for example, going up to 12 volts, up here, down here, up here. So this is the amplitude. This is the amplitude. Two different amplitudes. Here's a different amplitude. Here's a different amplitude. These two are the same amplitudes, etc. So now phase is like where it starts from or where it ends, I think. So like you have this waveform here, and then you can have another waveform here. Let's maybe if I copy it, duplicate. Yeah. So you'd say that these are the exact same waveforms. Let's just make it a different color. But these two, the black and the green, they're not in phase. I believe that's the case. I don't know that to be true, but I think it's the case. Let's see. Okay, so probably should delete this. Okay, when graphing a sine wave of voltage or current, the horizontal axis represents time. Okay, so this horizontal axis is time. Okay, events to the right of the graph take place later, while events to the left occur earlier. Sorry if you can hear the traffic outside. I've got the window open because it keeps me awake. I hate studying with the window closed. I don't know why. It's a bit like the whole coffee shop ambient sound thing. Quite like listening to the traffic, but I've got a noise filter on my mic, so hopefully you can't hear it. But if you can, I heard someone just beep just now, so you might have heard that. So apologies, but hopefully you don't mind, like me. All right. So what was he saying? So events on the right took place later, and events on the left took place earlier. That's quite. This is a good book. I'm telling you, this is a good book. So let's do this, right? You'll see what I'm doing in a minute. This is the good thing about the iPad as well. You're able to use different colors. Events on left take place earlier than events on the right. So you've got early, or you got like maybe let's do early first, later second, and then you've got last, and like I suppose later and last, just last, right? Yeah, it's not necessarily the end, but it's the end of what we tracked, right? Okay, so although time can be measured in seconds, it actually becomes more convenient to treat each cycle of a waveform as a complete time unit divisible by 360 degrees. Um, um, okay. So although time can be measured in seconds, so of course time can be measured in seconds, yes, it becomes more convenient to treat each cycle. Just get this in my head. So we've got a cycle. We're saying that we should treat each cycle as a complete time unit. So say like, for example, 0.2 nanoseconds. And then you just go, okay, you know, 0.2 nanoseconds, 0.2 nanoseconds, 0.2 nanoseconds. Is that what we're saying here? Or how are you getting divisible by 360 degrees? we talking about the unit circle here? Oh, okay. Because every single waveform here is divisible by 360 degrees. So you have, you know, 90 here, you got 90 here, you got 90 here, you got 90 here degrees. And then, you've got 360 here, 360 here, 360 here, 360 here. Do one more. 270, 270, 270, 270. Okay. So let's just write that down. It's a more convenient, more what? Can't spell. Convenient. You know how long I spent? I was so good in school learning like spelling. I used to kill it in all the spelling tests that we used to have. And now, who spells? I just type and I literally expect my phone to correct it for me. I don't even, when they recommend spelling, I don't even check. I just click, yep, correct that spelling. Okay. So more convenient. Uh, each cycle to treat each cycle of a waveform as a complete time unit of. So just I get that of the waveform. More convenient to treat each cycle as a complete time unit, divisible by 360 degrees. Okay. Where am I? I keep losing where I am. I should probably use my mouse to know where I am. A conventional starting point for counting in degrees is 0. The 0 point as the voltage or current begins a positive half cycle. Yeah, that's true. Okay, so what we're saying is that uh 0 degrees is also the starting point of each positive half cycle. Is the starting point of each half cycle. So you got waveform. This is 0 degrees. Starting point. Okay. So by measuring the AC cycle this way, it is possible to do calculations and record measurements in a way that is independent of frequency. So what's frequency again? Frequency. Okay, yeah. Because frequency is how many times it does it per second. But we're just saying, okay, forget about that then. We will look at it in terms of the positive peak being here at 90 degrees. Okay. So let's just put this here. This allows. So what I'm trying to do with these notes is that these notes that I'm writing here, they're not my final notes. These notes are my notes, my initial notes of what I'm studying, like lecture notes, for example. And then I take these notes and convert them into questions and flashcards and stuff for me to memorize and start putting to memory. So I will make a flashcard, for example, that says, you know, what's the benefit of starting of ignoring or what's the benefit of using 0 degrees or what's the benefit of having 0 degrees as the starting point of each cycle and treating each cycle as a complete time unit? Then it means that you can do calculations, independent of frequency. This allows calculations and measurements independent of frequency. Right. Okay. The positive peak voltage or current occurs at 90 degrees during a cycle. In other words, 90 degrees represents the phase of the AC peak. 90 degrees represents the phase. Okay, what? You haven't really explained what phase is here. The positive peak voltage or current occurs at 90 degrees during a cycle. In other words, 90 degrees represents the phase of the AC peak relative. I don't know why that means that. I don't get that. 90 degrees is keep losing where I am. 90 degrees is positive peak voltage. In other words, 90 degrees represents the phase of the AC peak relative. Things start to get complicated, cheers, when we need to relate two or more AC voltages or currents that are out of step with each other. By out of step, I mean that the two waveforms are not synchronized, that their peaks and zeros do not match up at the same points in time. The graph and figure below illustrates an example of this. Okay, so where does phase come into this? The two waves shown above are of the same amplitude and frequency, but they are out of step with each other. In technical terms, this is called a phase shift. Okay, I get that. The phase shift. What is phase? The phase of a periodic function of some real variable is an angle representing the number of periods. What? English, please, man. Defined by that variable. It is denoted and expressed in such a scale that it varies. I'm not even understanding that at all. In electronic signaling, phase is a definition of the position of a point in time. Phase is a definition of the position of a point in time on a waveform cycle. A complete cycle is defined as 360 degrees of phase, as shown in illustration A below. Okay. Phase can also be an expression of relative displacement between or among what? You know what? This is what makes university very difficult for a mature student. If you haven't been studying your whole constantly, until you got up to uni, and if you're 21 years old and you've been studying constantly since you was 4, that's, you're probably gonna understand this, but or your brain's probably just wired to get the kind of crap that these guys are coming out with. Like, come on, man, just explain things. An important characteristic of a sound wave is the phase. Phase specifies the location of a point. Phase specifies the location of a point within a wave cycle of a repetitive waveform. For most purposes, the phase differences between sound waves are important rather than the actual phases of the signal. When two sound waves combine, for example, the difference between the phase of the two waveforms is important in determining the resulting waveform. The phase difference between two sound waves of the same frequency moving past the fixed location is given by the time difference between the same positions within the wave cycles of two sounds. The peaks of positives going zero crossings, expressed as a fraction of one wave cycle. Two sound waves of the same frequency that are perfectly aligned have a phase difference of 0. Okay, so I think at the top here is probably the best definition I've got of it. Phase specifies the location of a point within a wave cycle. So, phase is a location of a point within a wave cycle. Of a point within a wave cycle. Phase is the location of a point within a wave cycle. Okay. So what's this? What are these guys saying? In other words, 90 degrees represents the phase of the AC peak. Okay, got it. So meaning the location. In other words, 90 degrees represents the location of the AC peak relative to the zero starting point. All right, I'm okay with that because you just said location. I get the idea to use the word phase, but tell me what the word phase means. So 90 degrees represents represents the phase of the AC peak relative to zero. Relative to zero. 90 degrees represents the phase of the AC peak relative to zero. Yep. Okay. All right. I got it. Where am I now? But yeah, it's really hard to keep where I am. Can I just highlight what I've done? That just keeps it more easier. Okay. Represents the phase of AC peak relative to the zero starting point. Phase relationships are also used to compare two AC voltages or current waveforms at the same frequency, as shown in figure 2.85b. This is B. No, this is B. What's B? 2.85, right? And then B, when two... Where's B? This one. When two waves of the same frequency start their cycles at slightly different times, the time difference of phase difference is measured in degrees. I'm confused because this is saying that this is B here. I don't get that because isn't this B? Well, this is about lagging, but they start at two different times. But these aren't the same. Or they have the same frequency because they complete their cycle in the same amount of time. They just have different amplitudes. Is that what we're saying here? Yeah, so they have different amplitudes, but they have the same frequency. The time difference or phase difference is measured in degrees. Okay, so there's a 45-degree difference there between them. So if you moved this second one, if you move this second waveform here back by 40 degrees, 45 degrees, then they would be exactly the same. All right, where was I? So phase relationships are also used to compare two AC voltages or current waveforms at the same frequency. So okay, got it. So comparing where am I? Comparing waveforms with same frequency. Okay. So let's try and draw this. And then how would I okay. How do you do it? That's okay. I don't know how to do this. Is that right? Don't know if that's right. Yeah, it's right. Yeah. Okay. Okay. All right. So what was he saying here? So phase relations are also used to compare two AC voltages or current waveforms at the same frequency. So these two have the same frequency but different amplitudes. They can be compared using, was it phase relationship. Phase relationships in degrees. Right, so what we say then, copy and paste this. So if we say that this is 0, this is 0, this is 90, this is 90, this is 270, 270. We've probably done these other ones in a different color. 0, 90, 270. Okay, so how are you working out that the difference here is 45? Okay, so basically from here, this point here is 45 degrees. Okay, so due to that, there's a 45-degree difference between starting points. I'm actually starting to feel incredibly smart here, and I get that this is super basic, but I watched this in my lectures on my first lecture, and I was beyond lost. So the fact that this is even starting to make sense to me is really amazing for me. Okay, and then so the same for here. Obviously, this is not to scale, not a good drawing. 45 degrees difference. And then, yeah, 5 degrees different. Make this smaller. So 40, all right, 45 degrees phase shift between two waveforms. All right. Okay, so since waveform B crosses the 0 point in the positive direction after A has already done so. So waveform B crosses the 0 point after A. Okay. There is a phase difference between the two waveforms. In this case, B lags A by 45 degrees. Okay. So let's do this. A and B. And what we can actually do is we can make the different colors so that clearly see they are A and B. This is cool, innit? The iPad is cool, I'm telling you. Okay, so just put here B lags A by 45 degrees. Got it? Alternatively, we can say that A leads B by 45 degrees. Okay, so obviously. Or A leads B by 45 degrees. Okay. If A and B occur in the same circuit, okay, yeah, of course, you can have different sources in one circuit. They add together, producing a composite sinusoidal waveform at an intermediate phase angle. You what? At an intermediate bloody hell, man. If A and oh dear, if A and B occur in the same circuit, they add together, producing a composite sinusoidal waveform at an intermediate phase angle. Wait, I don't even understand what words I'm using here. Let's try and use simple English. If A and B, if A, you know what? I've got a friend actually. He's an Iraqi guy, masters in civil engineering, and obviously English not being his first language, he was struggling with textbooks, and I completely get it. English is my first language, and I don't understand these English words at all. Okay, so if A and B occur in the same circuit, they add together, producing a joined together, suppose sine wave. Okay, and then what's at an intermediate phase angle? Just introduce phase angle. What is that? I've heard it before, but I don't know. So at a blur relative to the individual waveforms. So they produce a combined sine wave at blur relative to individual waveforms. I don't get what that means. I don't know what an intermediate phase angle is. Immediate phase angle. Love it. So at intermediate phase angles, the sum can vary over the range from 0 to 200%. At 120 or 240 degrees, the sum will be the same magnitude as either of the original values. Intermediate meaning just middle, like a middle phase. Is that what we're saying? Like intermediate, as in like, not beginner, not hard, just intermediate, a middle phase. If it just means middle, I'll accept that. I'm alright with that. Like this, right? Is this what you're saying here? You've got one, right? You've got another one, and the orange is the intermediate. Oh, okay. So in this instance here, for example, you would have, let's see if this is right. I'll be so happy if this is right. So here, you'd have, if when you add them together, you'd be in the middle here. Like this, right? But if this is correct, I'll end this video here. That I'll be happy. Is that right? If that's right, let's just Google adding two sine waves. Um, I don't know. I assume this is complex stuff. I think I'm dealing with baby stuff. Let's just continue with the book. This is all way over my head. Interestingly, adding any number of sine waves with the same frequency will always produce a sine wave of the same frequency. Though the magnitude and phase may be unique. The magnitude and phase. Phase. Okay. So do you have one where you add them two together? No? You're not gonna show us adding them two together? As one passes through 0, the other one reaches max value. This this one passes through 0, this reaches max value. Okay. But I would like to know how you're talking about adding together two sine waves. Where you haven't done that, just spoken about it as if I'm supposed to know. Like, show me what that means. A composite, let's just Google this. A composite sinusoidal waveform at an intermediate phase angle relative to the individual waveforms. Okay, here. That. Yeah. What's going on here? Okay. All right. Just show me two sine waves added together. I don't know what the problem is here. Uh, very frustrating. This is why like learning online is not the way to go. But you can't learn anything at university. So what do you do? I don't get it at all. Okay, you have to write down what it says and then just end this video here because I don't know if that's what that means. Who knows? Yeah. Okay. If A and B occur in the same circuit, they add together, producing. So I don't even know what to do. Adding waveforms. Um. If A and B are in same circuit, if A and B are in the same circuit, they add together, producing one waveform at an intermediate phase angle, whatever that means. At an intermediate phase angle. An intermediate phase angle relative to the individual waveforms. Relative to the individual waveforms. Okay, all I can hope for is that that somehow comes and smacks me in the face. I think it means that, but how do I know if they're not going to verify it in the book and tell me if I'm right or wrong? Then yeah, what can I do? Interestingly, adding any number of sine waves of the same frequency. So, what would be the same frequency? Like this, right? They complete their duty cycle. They complete the cycle in the same amount of time. Yeah, that's frequency, right? Yeah. So, excuse my yawning. Adding any number of sine waves of the same frequency will always produce a sine wave of the same frequency. Okay. So adding sine waves with same frequency equals same frequency output waveform. Okay. In figure 2.85c, we have a special case. In figure 2.85c, we have a special case. Okay, I read this. Where B lags A by 90 degrees. B cycle begins exactly 1/4 after A's. As one waveform passes through 0, the other just reaches its maximum. Okay. Okay, and then let's duplicate it. What we're saying here, saying that when one passes 0, the other one reaches its maximum. So this here passes 0, and this one reaches its maximum. Here it passes 0, this reaches its maximum. Here it passes 0, reaches its maximum. Okay. Okay, so 0. 0 point maximum 0 point maximum. Okay, let's do these in two different colors. Yellow. Yellow is B. Blue is A. Okay, so in this instance here, B lags A by 90 degrees when one waveform passes 0, the other reaches maximum value. Okay. All right, I'm quite comfortable with that. The only thing I'm a bit bummed out by is I don't know about, the adding the two together to get an intermediate phase angle. But other than that, I'm quite comfortable with all of this. All of that just took, was that an hour to do just one page? I take my time. It takes me a lot. It takes me a long time to get through these books. So yeah, but I'm learning, this is like I said, this is very tricky for me. So I'm very happy with the progress I'm making. If you enjoyed the video, leave a like, and yeah, I shall hopefully see you guys in the next video. Peace.